Hi guys, welcome back. So we're continuing this journey, and today we're in chapter 9. And chapter 9, as you can see, is advanced topics. So we're going to be touching upon, a few general topics uh, that I think it's important. Maybe for undergrads, it's knowing that something exists is actually very good. For grad students, I think it might worth your while to spend a few hours, maybe a few days, just going through each one of these topics, maybe try them yourself. So this is how I usually structure this chapter in my class. And this is actually a very good quote as well. So on the other hand, omitting things makes the model simpler, but the real world is complex. This is from Nick's book. I also have another one that we're gonna see once we put the PDF, which I think it's a very good resemblance of this project, of this chapter. So if you can see our chart here with the pipeline, the topics covered in this chapter could really fit into multiple portions of our journey. So I'm not highlighting a specific one, but it's also helps to see that we can always go back and think about these topics in different stages while we create this ML. So the main idea is really at this point in the course, you've seen it all. You've seen models, you've seen data, you've created models, you've tested them, you've explained them, and you've even done some causality analysis and stuff. So what was going in my mind is, well, let's just highlight a few things that are extra, that they're there, but they not maybe fall into like a like a cornerstone within our course slash needs for ML. We're going to be touching upon a few things. So we're going to be focusing a little bit on data. We're going to talk about synthetic data and augmented data. We'll talk a little bit about green ML. I'm sure you remember this from our discussion on energy and metrics, symbolic regression slash programming, genetic programming, and a little bit, tiny bit on ensembles. Once we go to the PDF, we'll see a few other things. And I'm hoping we're going to be able to cover maybe one or two softwares in this recording, this chapter. I know we covered a few in chapter 6, I think. So when we think about ML, we always think about data, and as we know, data can be expensive, can be hard to collect or measure. And hence we end up with some data that we call a data set, and from there, we start to build our models. And sometimes you see this a lot, actually. You see this data can make or break a machine learning model. So it becomes a question of, well, what if I have some data but not much of it? Can I do something about it? What if I have data that has a lot of class A but not much of class B? What can I do with these imbalanced data sets? So this is where synthetic data and augmented data come in handy. And synthetic data is creating new data or generating new data points by knowing something about the structure of your data. So from the data you already have, can we learn a little bit about this data and then maybe generate new data sets that do not really exist in reality, but however, they could be close enough to something that could exist. So the bottom line is the following. The new data doesn't exist because we haven't collected them. We're just creating them. And there's a good chance that this data actually exists. We don't have it. And the goal is really just to increase the number of maybe rows, the number of, in our data sets. So to do this, there are a few ways. And one of the, I think we have three. Yeah, we have three different methods. I think the slides have only two. The book will have the third one. I think the third one is a little bit extensive. I mean, to do. There's a lot of processing there. So this is why I kept out of the slides. I usually give the faculty the option to either cover it or not. But the simplest one is what I normally call conservative interpolation. And we also have another one that's called SMOT, or synthetic minority oversampling technique. So it's a technique that oversamples minority classes. Conservative interpolation is something also could work out well for interpolation between. So you have two data points, and you try to interpolate between these data points. Of course, assuming that there's a lot of assumptions going on there, and we could actually interpolate. What we're going to be doing is we're going to be showing, for instance, if you have a scatter plot like this, the dark dots are the space of data that we have, and the red ones are the data that we actually collected or our data set. Can we try to see, like, can we have more data? For instance, can we generate more data to improve our model? So conservative interpolation is something very, very simple. What we need to do is, if you think about classification, I think the one we discuss here, the examples I have are for classifications. I think you could use them for regression, but I don't have an example on those here. So let's say we have two classes, class A, class B, or failure, no failure. So what we do is we look at the data set and we pair them. So we look at the features and we try to pair the instances or the data points or the rows with similar features. So let's say you have two rows that have feature values that are very, very similar or even identical. However, one of the rows is for class A and the other one is for class B. What could also happen is you have the same thing, but both of them are class A or both of them are class B. So to simplify the process, let's just think about this out loud. Let's say we have two instances, and both of them have similar features or identical features. What can we say is, well, if we would have a third instance that happens to fall exactly between these 2 points. So we interpolate each feature and we look at the class, and if both original instances were class A, then the third one should be class A, big assumption, be careful. And if one of the classes is class A, if one of the instances is class A and the other one is class B, then we tend to take the worst case scenario for the new instance. So if you think about Pacheco's tests with concrete and spalling, let's say we have two instances, one spalls, the other one doesn't spall. Now I'm going to interpolate the features, and to give a class for this new instance, I'm going to say the following. Well, I'm going to say, there we go. I'm going to say, well, the worst case scenario for this feature is going to be the worst case class. And the worst case class is when concrete spalls or cracks or fails. So I'm going to label this interpolated row as class 2, which is failure. So this way I'm being a little bit conservative and hence conservative interpolation. Now, of course, you could take out the same approach and apply it for regression. You could say, somebody would say, well, maybe I'm being too conservative. Let's use the new class in this new instance as class A. Doesn't collapse, for instance. You could. As you know, we have assumptions. We have to make assumptions, and we have to live with them. And as long as we are very, very clear about this new generated data point, and we know it's synthetic data, it's something that we've generated, it's not something that we have seen. We could run the analysis with a big disclaimer saying, we had, let's say, 200 data points before, and then we added 100 data points that happened to be synthetic. Or we've added 20% of data synthetic data. As long as you separate those and you'll be very, very careful about this, then things become, a little bit more helpful. And one way to think about, did we do a good job or not is by looking at the following. So these are the real observations. You can see the min and max, with all the features and stuff, doing all the different features. You can now see the synthetic data. You can also see that there is very, very close resemblance. 152, 152, 03, 05, 511, 514, 11.7, 10.8. You can see 71.8, 1.6, 71, standard deviation 66. This is 1.3. So the numbers are close. They're not, very, very far from each other, but they're close enough. And if you look at the data set as overall, You can see this is 15207. The real one was 15203. 514, 4.9, 514, again, C ratio 11.7. Well, I have it now as 4.9. So you can see that there's going to be differences, a little bit differences. Averages 325, 326, 2.5, 2.3. Standard deviation 69, 71, 1.60 point. So overall, there is a lot of resemblance. Here and there, you're going to have some issues. For instance, let's see the case loading 0, 84, 5300, 4900. Oh, 5300. So a little bit resemblance there. 1342, 1556. So these are, could give you good confidence when it comes to knowing that will the new data set or the generated data set or subdata set actually have good features of the real data set. It doesn't have to be exact, but this is just a way for us to quickly check, do we really have enough similarity between the data, between the real data and the newly generated data? And my advice is we don't really know how good is good enough. So is 0.1 difference is fine, like 10% difference is fine, 50% difference is fine. So my advice is always to practice, create a few things. It doesn't have to be always the average. You could do, what will I feel very, very good about the data I've measured from class 1, much more confidently versus the data I've collected for class B. Maybe it came from a different lab, different equipment. So I'm gonna place a little bit more weight on class A. So instead of just averaging or interpolating, I'm going to say the new data point is, I don't know, 75% from class A, 25% from class B. It's very fluid, very flexible. And it has to go a lot with, with what we have, what we have in our data. Now, of course, another way is to use a smart, and smart is actually very, very cool. Let's say we have something like this. So we have two classes. We have a class that we have a lot of data points from. So let's say the red class here is a majority class, so we have too many points from it. And we have the blue class, which is the minority class, not as much data. What Smart does is it says, well, if I'm going to be using this data set, well, this is a clearly imbalanced data set because I have too many data points from one class versus the other one. So what I'm going to do is I'm going to try to create those new data points that only happen to be the minority class, and hence the minority, the title of Smart. And when I do this, I'm creating new data points, but the data points, the new ones, they have a purpose. The purpose is to improve the number of points within the minority class. In the first example, we have conservative interpolation. The goal was just to generate, make the data set a little bit larger. In this case, no, I'm going to have to create new data points for the case of improving the minority class. So how do we do this? Well, in general, without going into too much math, I'm going to be looking at these data points. I'm going to be finding distances, and I'm going to find, let's say, the average distance or the Manhattan distance or something with a distance metric format. And I'm going to give it like a ratio between 0 and 1, let's say 0.2. So find the distances, multiply by 0.2. Here you go. We have a point here. We have a point there using, let's say, these 3 points. Here we have this point using these 2 points, these 3 points. You could use 2 points, 3 points, 4 points. It's really gonna be up to you. Now, how do we know that these points are actually good? Well, we can do what we just did earlier by looking at the min, max, range of data, or we can do something a little bit more advanced here. Let's say I'm gonna have the correlation matrix for the real data, correlation matrix for the fake data, and I'm gonna plot the differences in a new matrix. So if you look at the colors, you can see there is a lot of resemblance here between these two matrices, which tells us that for some reason, somehow that we have good match between the new data and the fake data. Of course, you can always have some issues. For instance, here you have, if you look at this and you look at this, we have 3. You can see that the shades are a little bit different. If you look at different shades also, we also have maybe maybe here. It's a little bit lighter than here. And you can easily see the difference here. So this one tells us, well, the biggest difference is actually here and here. So you go back and see, you know what, between the F prime C and the loading, I have a big difference. However, this difference is about 0.3, so maybe this is small enough, maybe it's not small enough, so you always go back and update the data. So this is another way that we can check and see, do we have enough, good similarity between the real data and the generated data. There are also other methods, but the goal that we have to remember is the following. When you create fake data or generated data, the data itself, the data point itself doesn't exist. So we have to remember that. That doesn't mean that we're improving our data set by having realistic data. This means that we're having a new data set that happen to have similarity that could possibly be existing if this was a real data point. So this is one thing to always remember. So this is the goal from synthetic data. It's generating something new. Now, augmented data is where we do the following. So we take some images, let's say from real tests, and then we build a finite element model that give us different images, right? And we call these augmented data because we created them using, an augmentation method or a simulation method. We could do the same thing for images. We could do the same thing also for, let's say, if this is beams, you can create finite element models for beams and use the data from the beams and from the simulations as augmented data, because these data were more or less created based on verification of simulations. What we always need to remember is always, of course, generated data is not real, so this is the biggest item. Another thing that we have to remember whenever we use simulated data, whenever you use simulations, you have to impose idealizations, you have to impose boundary conditions, element types, meshing, and stuff. So there is a lot of idealizations that we will get from simulation. And when you take those and put them like with the data that has some randomness from tests, this might lead to a little bit of a biased data set, not a big degree, but it could be significant in some cases. And we just have to be aware that synthetic data have issues, they don't exist. Augmented data are much more likely to exist since we're using some form of physics or mechanics to generate these. However, overall, they might suffer on the idealization item because everything seems to be perfect when you do a finite element model. In real life, it's not that perfect. And sometimes some phenomena are very, very hard to model. For instance, charring is very hard to model. Spawning is extremely hard to model. So somebody would say, can I create finite element models of these things? You could, but charring is tough. Spawning is also tough to model. So augmented data may not be something that's very helpful, even synthetic data. So if somebody would like to find, I don't know, let's say cracking in a beam at ambient temperature using synthetic data, my confidence would be much, much higher than doing the same thing for a beam under fire, just because we know that under fire things are much, much more complex than at ambient temperature. And hence, I would be much more worried about synthetic data use / idealization use when the phenomena is a little bit complex versus when the phenomena is a little bit easier to deal with. So keep that in mind. You could use these. I think I have the codes for these in the appendix, which is online. You can access that. You don't have to get the book for that. And all of this data, we have an Excel sheet for it too, so you can download those and try to experiment with them. Moving to the next topic, grid map. So when we talked about the metrics, we emphasized that some models could actually use a lot of energy when you create them. And this energy could be massive, and massive is usually a good thing to put some numbers into it. So for some deep learning models, they generate between 6 and 1,000 kilograms of emissions CO2. And they could cost somewhere between $41 to $3.2 million per model. This is how expensive these things can be. If you want to compare these numbers to things that we can, quantify, I think a human contributes to about 5K of kilograms a year. And 150 kilogram of carbon a year is equivalent to the lifetime of 5 fuel-based vehicles. So if you have 5 cars and you drive them all the way until they break, this is how much 100,000 kilograms of carbon would look like. A lot. Sometimes, which I find interesting, is something like this. So somebody creates a model, it works well, then they create the next gen model or the new generation model, the improved model. Its accuracy improves, so the accuracy of ResNext, so the first model was ResNet. It had a good accuracy. Then ResNext was the second model, and ResNext improved accuracy was 0.5% improvement accuracy, which is improvement. However, ResNext used 35% more energy to get that 0.5% improvement in accuracy. So this is hopefully now when you start to think about, well, okay, shall we go back to the example where we talked about 97% R square versus 94% R square? Does it, 94% R square with less energy versus 97% square with high consumed energy, let's say 15% more than that simple model? Does it make sense to use the more expensive model or not? Maybe it does, maybe it doesn't. So a lot of these things are problem dependent, and it helps a lot to visualize these numbers because then you can see, okay, well, it's a new model. Uh, it works much better. I have 0.5% improvement in accuracy, but energy-wise, 35%, that's a lot. That's a lot. Yep, this is like another way of talking about the same example we talked about. I like this example. So I do a lot of work with roof construction materials, if you may. And something would say, let's say, if you create a machine learning model that can give you predictions of 38 megapascal plus or minus 10%, do you think that this is going to be something substantial, or do you think we should really get a model that can give us 38 megapascal with plus or minus, I don't know, with more energy? Well, the way to think about it is the following. If the difference is 10% max, so this is about 3.8 MPa or 4 MPa. So at max, we can get something like 40, 42. At least we can get something maybe 34 or something. Both of any of these concretes are still normal strength concrete. The mix probably won't change much. So is it worth it? For this particular case, it may not be worth it, but like if somebody is doing something else, let's say somebody is trying to measure the mercury in water, or like pollutant in air, you might want to be very, very accurate, right? Because the dosages makes a big difference. Reliability also is different. So one way to visualize these differences is we had a case study. So a little bit here so we can see that. So we've tested, I believe, 11 algorithm or 12 algorithms. And we have 3 metrics. So we have accuracy, we have AUC, and we have LLE. And this was a big data set, 8,000, about 10,000, 8,000 concrete mixes, and we were just trying to label them. Do we have good mix or bad mix or poor mix? So if you try those 11 algorithms, you see that almost all of them, with default values, they achieve 98% accuracy, except one here for training, KDS. So if you take this one out, we have about 10 algorithms or so that they all achieve 98% accuracy, all of them. If you look at AUC, all of them achieved, I believe, more than 98%. LLE, most of them are within 5%. You only have this one and these a little bit here. So you can say all of them are less than 10%. That's very good accuracy for default values for a significant larger data set. You could basically use any model. But if you start to look at model size, training time, prediction time, you can see now there's going to be some differences. So model size is, usually simpler models, GPTs, they don't contain much trees, they don't contain much trees. LGBMs, XGBoost, but they have a lot of size. Training time again. KDs, they take a lot of time. Simpler models, time. Random forest, for instance, in this case, relatively small. If you think about prediction time, again, smaller models. Random forest takes a lot of time because you have to decide between all the trees. GPT, again, between all the trees. XGBoost is a little bit fast. LGBM is much faster. So if you think about the composite metric for all of these, you can find that for similar data set, for these accuracies and AUCs and performance, this is how you can rank these models. So basically, somebody would say, well, the best one to go is maybe logistic regression. It consumes the least energy and it has good accuracy, more than 95%, 98%, which is great. So this is one good example of using simple models and versus more complex or exotic models like LGBMs and XGBoost and stuff. And you wouldn't know this if you didn't try multiple algorithms. So my advice is always to try multiple algorithms. You never know what you're gonna find. This was another example here. This is the same case study, but you can see the difference in predictivity, accuracy versus energy. So you can see some models they consume a lot of energy, but they have very, very low predictivity. You can see a model here, it uses predictivity and energy almost good trade-off here. This is high accuracy, but 60% normalized energy was XGBoost. Here is LR. So out of all the models, it has the least energy and it has very, very decent predictivity because I'm normalizing everything with respect to the largest model. And we saw the difference in accuracy is very small. So we're really dealing with a lot of percentages there. Now, of course, if you're more interested in calculating energies and carbon and stuff, you could easily do the math here. I also have it in this paper, so we have you could do that. But my goal, I believe, from this example was if we have, let's say, if we use a typical computer, like an average computer, how much CE would actually produce, right? So I came up with this. If you go to ASCE, I believe they estimate about 150,000, 150,000 civil engineers. This is how much we are around the world. Let's say 1%, 1% of us use ML. The 1% of all of us use ML, and an average computer would generate this much kilowatts per hour. Let's say 126. I think the top of the line is about 300 as of 2022, I think. So this is how much energy of carbon we can create a year. About 41 passenger cars. That's a lot. Driven for 1 year. Not to their end life, but just for 1 year. That's a lot of carbon. Well, somebody would say, well, oh, this is a lot. Well, what are we doing here, right? Well, here's the funny part. Here's the funny part. If you compare this to how many energy you can generate from creating software, I mean, finite element softwares, it's massive. Finite element. Just you can do the math. You can actually follow the math here. But just by storing, not even by creating the FE model, just by storing the model, we're creating, I believe, more than 200 times larger energy than a machine learning. Very rough estimates, of course. The point is the following. The point is, although machine learning uses energy, FE also uses energy. Testing also uses energy. There is a lot of energy being used, but it would be great if we can reduce this energy. for instance, come up with ways to make softwares or like FEs a bit more efficient. Same thing for ML, make them a bit more efficient. For ML, having something like this, like a sensitivity study, where you first identify a good trade-off for accuracy, balance, energy, and then going for that software, for that applicate, for that algorithm, would be much better than just jumping into a more exotic, much more complex model and hoping for the best, right? Perfect. I believe this is everything we had in mind for green ML. Symbolic regression. So the third, we're almost done with it. This should be a very short chapter. Symbolic regression is the following. We talked about this when we talked about genetic algorithms, I believe in chapter 4 or chapter 3. Symbolic regression is a form of regression where the form itself, the equation format, is not given to us. So we have features. Let's say we have feature 1, feature 2, feature 3, feature 3. And we don't know what's in between. So in symbolic regression, we're trying to find the relationship between the features as well as the form of the equation. So this could be, for instance, multiplication, this could be division, it could be plus or minus, and this one could be like, cosine something. So you're basically searching the space of mathematical expressions, plus, minus, cosine, sine, and operators to derive an expression. So you're trying to come up with a new expression. And this is usually something interesting because the model itself does the analysis for us, and we end up with an equation, and then we use the equation then. So instead of reusing the model every time, we'll just have an equation, we can just substitute in the equation. This way, you're only using machine learning once to come up with the equation. If you're using decision tree and you would like to predict something, you have to reuse the decision tree. Same thing with XGBoost or deep learning. You always have to use the model, to run the model one more time. In symbolic regression, you're just using the algorithm to find the expression. And then once you have it, you can just, hand substitute or like plug it into Excel and just use it. And that'll be faster and easier. Plus, you can see the relationship between the equations. So there are many ways to carrying out symbolic regression. One of the easiest ones is you could say something like the survival of the fittest, where expressions compete, and the best performing expression goes to the next stage, and so on. So it's we always try different expressions, and only the best one survives. And there are many ways what we could use. That could find two expressions and cross match them, or we could find a very good expression and try to modify the operators within the expression to make it a little bit better, fine tune the coefficients, and so on and so forth. And an easy way to visualize this is actually by practicing. And I do have, I know we saw this in the previous, in the chapter 6, I believe. But just in case we missed that, let me bring in my browser. No. So let's see. Sure. Yes, we are. So this was made by Facebook, by Meta. I think Pierre yeah, Pierre and Francois. I think they were kind enough to make this platform and share it online with all of us. So it's end-to-end symbolic regression with transformers, and this is based on deep learning. So they have their papers here, you can see them. And if you would like to try something, you could say you will upload a CSV file. You can bring in your file, drop it there. You can see here the analysis is being run. Give it a few seconds. And here you go. Now you have this expression where x0, x1, x4 are the features. And this expression have an accuracy of R squared of 0.96. And as you guessed it, this was the expression to find, or the symbolic regression expression for the problem we did in chapter 3 when we have those steel tube columns with concrete, so we're trying to find their axial capacity. Very, very simple. You can, I think the trick here is to use a SCV file that's with delimited commas for this one to work. And make sure that you don't have any feature names. So the first row should not include any feature names. You could also try like your own expression. There you go. It shows you the predictions, also plots some nice plots. You could try randomly generating some mathematical function. Give it a few seconds, it will run, and you'll have a very nice expression. There you go, 88% accuracy or R squared. So these are very, very easy to, you can try them in your data set. What I usually have, I have like some of the data I have online for like in the appendix, we usually try this in class, and I divide the students into groups, and then each group tend to find like the most accurate expression. Oh, yes, before we go. I also have this Heuristic Labs. So Heuristic Labs is a software that you can download for free. I think it's based on Germany. Yes, they also were kind enough they have it as open access, and they were kind enough to let me discuss it in my book. So let me see what we are. I also have it here. Let me see if I can bring that one up too. Yes. So this is how it looks like, Heuristic Labs. So what you do is you actually go and you could just pick the file. I have it here. It's just a CV, the same model, the same data we use before. You could try to change, for instance, if you want to use like different evaluators, if you want to use different fitness functions, different validations. If you go to this tab here, you can actually start to play with the algorithm. So you can say, well, I want 50 generations, 100 generations, 200 generations. I would like the mutations to be 15%, 10%, and so on. You could try all these different options. What I normally do is the following. I like to keep things very, very simple. So I put the data, and I just run it with default values just to see what's going on. So here in this case, once you execute the run, it took me 12 seconds to run this analysis. You go to the results. Usually the results stops here, so you can see the generation. What you need to go is you can go for the best training solution, and then you can go to the symbolic regression model. It looks like this. What you also would do, you could export the model to Excel, or you could simplify the model. What I like to do is you go right click and you go for the mathematical representation, and here is your equation. It's a little bit more lengthy than the other one, but this is one way. And as you can see, you have all the constants here. Now, what's the performance of this model? Well, the performance, as you can see it here, so you have the absolute mean error, training, mean square for training and testing, and you also have R square. So R square is 0.965 for testing, 0.94 for training. You can also see very partial dependence plot. Let me see if I can make this a little bit further. Partial dependence plots. You can export that to Excel. You can see the residual and oops. Yeah, you can see the training and testing. Scatter plots. This is, for instance, for training. You can see for all data. You can see for test as well. Very easy to navigate. Well, we don't really need error here because this was a regression problem. Density, let's see, let's do test. Oh, keep this as 2. So you can see this is now the features with the axial capacity for partial dependence plots. For heuristic, you don't really. Yes, for heuristics, you can have the labels. So the first row can have the labels for each feature. I think the one in meta still doesn't take into account the labeling item. all these are important. So what usually happens if you get stuck, try to update the number of generation, and you can maybe just play with the mutation a little bit. You can see the operators, you can see the engines, and one thing here is if you run multiple cases, they tend to save the expressions. I like this a lot because you can export this into Excel. Oops, and you also have here different local problems. So for this particular case, I went for geometric programming, symbolic regression. Could also do geometric programming, symbolic classification too. It does both. It also has a lot of cases, a lot of algorithms, table search, simulated annealing, scatter search. It has a multiple of things that can be helpful. And they have a very active help group also in Google, I believe. They're very kind. Yeah, there's also Turing part. I haven't reached out to them, so I mean I've did, I haven't heard from them, so I wasn't sure if I can share this and upload it. So I'm trying to avoid that. But it's also a very neat software that you could try. The very last portion of these slides are ensembles, and we've seen this theory before. The no free lunch theorem, which says not all algorithms. We don't really have one that's best. The average of all seems to be the average, or simply there isn't one single best algorithm. So because of that, what we could do is we could try different algorithms, like I showed you in the previous example up there, or even better, let's say out of the algorithms we chose or we selected, we tried, how about we use the top three or top five or top 10 and we combine them together? Now, when we combine algorithms together, what we're doing is we're improving their accuracy. And plus, we're overcoming each of their limitations because now the group is better, most of the time, perform better than the single algorithm. So this is what ensembling is, combining, trying to combine algorithms. How do we combine? Question becomes, well, we know combining seems to be good. Well, how do you combine? Well, in regression, the simplest form is actually to average the predictions. So if you have three algorithms, take the prediction of each algorithm and average it. That'll be the best thing. In classification, same thing. But remember, in classification, we actually have votes. So you could take the average vote, you could take a weighted vote. For instance, if you know that model one's accuracy is 95%, models two accuracy is 96%, models three accuracy is 60%. Well, you know for sure that model one and two have higher accuracy, so you may give them a little bit more weight than versus model three. So it's a little bit flexible. And again, anything that's flexible is usually you get to have a lot of room to try and pick and choose what to go from there. Don't be shy. Try multiple things. Don't be afraid to try to combine things because at this point in time we don't really have like very hardcore rules on what to combine, how to combine. Ensembles also come in different types. We have stacking. So stacking means we're just combining prediction. You can combine and average them. We also have blending. Blending is very similar to stacking, but we use the handout, the holdover set, the one that we didn't use in training to make prediction. We also have bagging, and bagging is a form of bootstrapping. And bootstrapping is when we create parallel models, and the models tend to learn the error from each other. So you're becoming better because you're learning the errors. We also have boosting. Boosting is you start with very weaker models, and you continue to train them and teach them on how to be, better models. So you go back and you keep running the errors or the instances that took a long time to be predicted correctly. Show to them and show to them until they become model better. So it could be something like this. For instance, you have data, you have model one data, model two data, model three. So you continue taking the predictions from different models and combining them together. This is where I stop having the slides, but I want to just emphasize there are more topics in the PDF, and I try to avoid these in my slides. I mean, I just feel this chapter would be very lengthy. So what I do is in class, I usually go over over the other things, because for my class, the students you have, what, like, if they have done research or not, how interested they were, and from there you could decide, okay, maybe I have maybe one or two lectures where I can dive into more ensembling or more practice or other things. I'm always afraid that if I show like too many things in a recording, and the recording, I mean, my recordings tend to be awfully long. I'm trying to keep them within 60 minutes. I just tend to uh, lose my audience a little bit, and this is why I'm always hesitant of describing every single thing there is, because I don't think there is really um, may not be as beneficial as just highlighting the big items or the thing that you would mostly see and use. The other cases might be too specific for a specific problem, for a specific case, where you have to spend a little bit more time in understanding those. So we've talked about these. We've talked about this one, small. So we also can use GANs. And let me show you. The GANs were not in the slides, but we have them here. Yeah, something like this, where you could compare the real data to the fake data, and you see the distributions that they're actually, there's good agreement there. So it gives us a little bit more confidence in our fake data. You can see FY is a little bit off with the measurement between the real and fake. We can also still use those uh, differences. I have all the Pythons and stuff within the bug. Remember, whenever we're dealing with data, we have to remember idealization. This is something big that we have to be careful of. Yeah, we've talked about these. Yeah, this notion we didn't talk about in the slides. So, we have simple models, we also have complex models, and we have exotic models. Complex models, I define them as ones that you have ensembling. There's some kind of combination there, more than one algorithm. Exotic ones, usually we use them a lot in optimizations. And this is when you have a model, like a machine learning model, and then you use another model to tune the model, the first model. So there is going to be distinct models applied. Most likely one of them is trying to optimize or tune the other one. In complex models, they both predict, and we find some form of a prediction strategy to combine both predictions. So this is how I distinguish between these two. This is the same example we've seen before, except I just have here a little bit more figures to show the predictivity and stuff. So in this case, you can easily see that XGBoost has the highest predictivity comparatively. But once you look at the energy-wise, and this is how you can use data robot for those things. When you look at energy-wise, you can see it's about 2/3 down. Logistic regression actually has the lowest energy, which makes a lot of sense because it's a very, very simple model. Yeah, I found this interesting. I know I don't have it there. I just feel this is a little bit advanced. So what I did, part of the comparison or the parametric study was we're gonna be using similar models, I mean similar algorithms, but different languages. So I'm gonna use random forest from Python, random forest from R, GPT from R, GPT from Python. And the goal is to compare if I use the same identical algorithm but different languages, does it have an effect on productivity or energy? And the answer is actually it does. In random forest, maybe not so much, but in GPT, there is a very clear difference between productivity and energy for the different types of languages. Same thing here. If you use the same model, say KDNN, but different architecture. So this is one layer, 64 neurons, 3 layers, 2 layers, one layer, 1536 neurons. So you can see there is also a big difference within the same algorithm but different architecture, which I found interesting. A larger comparison. Yeah, this chapter is a little bit laid out differently than the other chapters. For instance, every section starts with the subsection called big ideas, and it ends with a note. And the note is usually some of the things that you have to keep in mind when it comes to this particular uh, big idea. Yeah, we've seen those. Eureka was a very good software. It's been bought by DataRobot, I think, a few years ago. So it may not be readily available, but now they have it within data. So once we go to the DataRobot, we've done that already. In that chapter, you can see that there are Eureka models there that we could use. But this is the interface for the original software. Yeah, you can see the versions I use. So there are also other things that I was hoping to try to use, GB tips or D. D is very hard to find now. GB tips is still out there. Yeah, it was, you could easily pick and choose the operators and stuff. This is the ZFY problem, the moment problem. Once you easily find the expression M equals ZFY as easy as this, very, very quick, very quickly. It's small form Turing part is also there. With the heuristics lab is also there. We've seen this. Yeah, in heuristics you can also choose and pick and choose the types of uh, operators. Actually, I can show you this since we already have the thing. Go back here for a minute. I think if you go to algorithm, maybe. There we go. So if you go to the problem, then symbolic expression tree grammar, you can say, well, I don't want to have any additions. I don't want to have any subtractions, or maybe you do. You can say, well, I want to have some power functions. I want to have some conditional symbols. I want to have some binary functions and special functions and stuff. You could also add and remove these. These softwares are very, very flexible and makes our life a little bit easier. Yeah. So this is the problem with this is the same problem with moment. Moment equals fy. In this case, exponential, log, a constant z, constant plus constant. So you can see that expression is different for the same data set, which was surprising. Then you could simplify, and then eventually it would be fyz times plus some error. The error is very, very small. You can see c naught is negative 3.6 e to the negative 12, which basically tells us moment equals fyz. So you always start with a complex model, and then once you simplify, there's a very good chance if the problem is well defined, you're going to arrive at a physical problem, a physical expression. Gene Explorer is also good. They were kind enough to let me use the software. Very easy to use. What I like about this one, as I said before, you can do the analysis, and it gives you the script for Python or C++ or C, so you can just copy it and use it directly. You don't really have to code anymore. This is Metas. It used to be dark theme. Now it's a lighter theme. And of course, we have the Python and R stuff. You could copy these codes and try it. What else do we have? Mapping functions are important. They're just I feel this is a little bit complex for this recording. So I'm not trying to avoiding it. I have a few papers on it, but I don't think this is a undergrad, even for grads. This is a little bit for higher end grad students. So you could read it. I think it's interesting, but it's not something that I would like you to focus on that much. This is oh yeah. So this is good. What we did here, I know this is like one of the simplest problem there is, moment equals fyz. So if you try different algorithms, this is what you find. You see that there is a lot of emphasis, feature importance wise, on z, and not so much on fy. And if you look at the equation, it says fyz, so it's about 50-50 equivalence. And this happens because of a very simple fact that whenever we use z from the manual, there is a lot of z's. But if why there is only a few grades of steel for beams, and hence the importance, the model think the importance is much smaller. In reality, it's not. It's an equivalent importance. But because the data we have only uses a few grades of steel versus many Z's or many sections, the model thinks it's, Fy doesn't have as much importance as Z has. And this is one of the things where you're going to have to be very careful with explaining your model. Yep. Oh, let me show you this. So if you go to data robot, you can easily see Eureka. You can find the expressions as well. Yeah, this is FYZ. I don't know why my PDF is oh, it's 150%. Maybe if I, yeah, oh yeah, FYZ. You can see that. Yeah, different problems as well. Here, you can try this. Ensembles are there. Ensembles are very easy to do with data robot. Yeah, for data robot, because all what you have to do is you can say create blunders. So under additional, you go to create blunders, and then it automatically creates ensembles for you by choosing the top 3 algorithm. You can also pick and choose the ones you'd like to use. Big ML, yeah, very nice. Very kind to me too. They all actually were very responsive when I reached out to them to showcase the softwares. And a lot of these things they have just like what we talked in the previous chapter. They have easily allow you to use their platforms. AutoML is basically something we talked about this a little bit before, like with the chapter 6 with the platforms. It's basically the idea of, well, if everything can be automated, how about we also automate the whole process? And you can have the interface like BigML, Data Robot, and these ones where everything is there. You just have to add your data and you click, voila, you have a machine learning model. And you can verify it, you can test it, you can explain it, you can do all the fancy things that you need. You can even deploy it now. This was Clemson. It's our own like in-house architecture. Took a while to get it done, but hopefully, yep, this is if you're MDR. There we go. This is a bad exam at 45%. This is not very good prediction. And this is good, so much better. 55. You can see that it's barely catching. You have a lot of there. Again, if you look at feature importance, you see a lot of insights. You can even plot everything. So this is Clemson's interface. The class project, energy consumption. This number 9.4 is usually a good homework problem. A good homework problem. Yeah. That's it. We only have chapter 10 and chapter 11. 11 is very short, so we really have chapter 10. But as always, guys, hopefully this was helpful. Hopefully it was enjoyable. Hopefully I'm within the 60-minute miss I started earlier. And if you have any questions, please reach out to me. Best of luck with everything. And hopefully I'll be hearing from you soon. Take care. Oops.